So now we want to rework these problems using the shortcut method. And to understand the shortcut, first thing you have to understand is the chain rule. We talked about it before that the last thing you do when you take the derivative of a parentheses to a power is you multiply by the derivative of the inside. So in integration, technically, because it's the reverse, it should be okay to just divide by the derivative of the inside first. The problem is it doesn't always work out perfectly like that. If there are variables involved on the inner derivative, it's not there. It's just not as easy to see. So I need you to be able to look at it in a certain way. So to train you to look at that, we're going to come up with a little story. But before we do that, where does this go when you integrate?
It cancels out.
Where does it go? Like if we just integrate the integral of x dx, where does he go?
Away.
He goes away, right?
Yeah.
He goes to the integral gods. That's where he goes. Okay? So the integral gods are what allow you to reverse differentiation and bring it back to the original. So they're basically what they allow you to integrate, okay? And they require a sacrifice. And the most basic sacrifice they require at a minimum is the dx, okay? So you don't know it, but you've always been making these sacrifices. This little guy goes whoosh over here, and over there where you can't see it is the integral god volcano. And so before you integrate every time, the integral god volcano eats this dx. Now they're not very powerful gods, okay? So they can't take major sacrifices, just some basic ones. But they can take a dx, okay? They take that, they let you integrate, life goes on. Got it? Okay. And that's because of the chain rule reversal there, basically. I mean, that's really honestly, mathematically, that's where it's going. The chain rule reverses itself, boop, the derivative disappears, and you're allowed to integrate, okay? But we're going to sacrifice to the integral god. So if you don't have a parentheses to a power, that's the only sacrifice you have to make, and boom, you're allowed to integrate. But when you have a parentheses to a power, such as this example, you have to sacrifice not only the dx, but the derivative of the inside of that parentheses. And so the derivative of the inside of this parentheses is 3. I don't have a 3 to give away, but I need to give a 3 and a dx to the integral gods. If I do that, they will allow me to add 1 to the power of the entire parentheses and divide by the new power if I make the sacrifice of the dx and the derivative of the inside. But as we said before, they're not particularly sophisticated gods. Okay, they don't really have any power other than integration. So we can trick them. And what we do to trick them is we just make up a 3. You just pull it out of thin air and you be like, you know what, integral gods, here it is. Here's a 3. So take this 3 right here and this dx and let me integrate this problem. So we made it up. And you can do that. The integral gods don't mind. But the math teachers do mind. Y'all understand that, right? Okay, so mathematically we can't just really make up a 3, but we can always multiply by a what in math? A 1. So if I multiply by a 3, if I also multiplied by a 1/3, that technically wouldn't really be changing the problem, right? So to balance this 3 that I made up, I'm going to put a 1/3 in front. And if you look at that, that really hasn't changed the value of anything. So far, so good? Okay, so if I made up a -2, I would put a -1/2 in front. If I made up a 2/5, I would put a 5/2 in front. That's to balance it. Kind of like balancing chemical equations. Okay? You got to keep them balanced. So I had to make up the 3 because I needed to give away the derivative of the inside. And so here's what happens. Once you have this to give away, and you sacrifice it to the integral gods volcano, they will give you the power to just add 1 to the whole parentheses and divide by the new power. So now we have 1/3, 3x minus 5 to the 5th over 5 plus c, which is 3x minus 5 to the 5th over 15 plus c. And that's the same thing we got when we did u substitution, right? Mm-hmm. Okay, now your book doesn't talk about integral gods. Your book talks about UDU patterns, okay? So even though they don't always do u substitution, they look at it and they say, all right, if this is u, du is not just dx. I need a 3 to go with it, the derivative of the inside. And so they talk about it that way. But I kind of like the little backstory because it reminds me to make the sacrifice every time before I integrate and I don't forget. Make sense?
Mm-hmm.
Okay, so you guys try the second one and see if you can get the same answer again, but not by substitution. Okay, so for the second one, if I want to integrate without doing substitution, I have to appease the integral gods. And I do that by giving away to them the derivative of the inside of the parentheses. And that will allow me to integrate that whole parentheses to a power. So I need to give away a -5, right? And of course the dx, that you always have to sacrifice that. So I'm going to make up a -5, and I'm just going to stick it here with the dx. So that's going to be my sacrifice. But if I make up a -5, I have to balance it out front with a -1/5. Once I sacrifice this and reverse the chain rule, I can just add 1 to the power and divide by the new power. So I have -1/5 2 minus 5x cubed all over 3 plus c. And see that we got the exact same thing as we did the first time without all the trouble. Now some people don't like this. I don't know why. They prefer to go through using substitution, and that's okay. Any questions? No? Let's try one more before we break this. Let's talk about these guys. They're a little different because they look a little more complicated. First one has the integral of 2 over 2x plus 3 cubed dx. So you do see that we have a parentheses there, right? But before we can work with it, we need to bring it up to the top. So the first thing we're going to do is rewrite it as 2 times 2x plus 3 to the -3 power with respect to x. So even if I wanted to distribute here, I couldn't. Like I have a -3 power, and you can't distribute a -3 power. You guys understand that? Not to a binomial. So I'm going to try to use sacrifice or substitution. Which do you want? Sacrifice? Okay, so we're going to try to give away the derivative of the inside. What do I need to give away?
2.
A 2. It just so happens, well, I need to give away a 2 and a dx. It just so happens I already have a 2. Why don't we just give them that one instead of making up another one? But if you really want to make up another one, knock yourself out, okay? You can make up another one and balance it. I prefer if I already have it just to give it away. So we're going to take this guy, we're going to rearrange it, we're going to put it over here so that the integral gods can see that we have put our sacrifice on display for them. And off he goes into the volcano. And we are now allowed to add 1 to the power and divide by the new power because we made the correct sacrifice. Add 1 to the power, divide by the new power, clean him up. Am I allowed to leave a negative exponent?
Mm-hmm.
Bummer. So that has to drop back to the denominator.
Mm-hmm.
So that's going to give me a negative. There's already a 2 on bottom. That'll go to the bottom. And what's left on top? A 1. So really, once you practice this a little bit, it gets really fast. The key is just don't go so fast that you forget to make the proper sacrifice. That will allow you to reverse the chain rule and integrate the parentheses to a power.
So if you already have like the 2 there, you don't have to do the fraction.
You don't have to make it up.
Okay.
You only have to balance it if you make it up.
Okay.
And there's another limitation we haven't talked about yet. You're only allowed to make up numbers. If you need to make up an x, you can't do it. You have to find another way. That is the limitation to the sacrifice method, okay? If you need a variable and you already have one, you can use it. But if you have to make up a variable to get what you need, you're not allowed to make up variables. You'll have to resort to substitution, okay? All right, you guys try this one. The integral of the square root of 3x minus 7 dx. And remember, you first need to look at it in parentheses form so that you can see it in exponential form and go from there. Okay, so the first thing we'll do is we'll rewrite it as 3x minus 7 to the 1/2 power. And I'm going to leave some room here because it's a parentheses to a power, I may have to make up something. So I need to give away or sacrifice to the integral gods what? 3 dx. Agreed? You have to give away the dx and you have to give away the 3. So we're going to make up a 3 because I don't already have one. So this piece whoosh, into the volcano of doom. And that will allow me to just treat this like a monomial. And that will become 3x minus 7 to the 3/2 divided by 3/2, which is multiplied by 2/3 plus c. See how easy that was?
Did you not have to multiply by 1/3?
Oh man, that was too easy, wasn't it? What did I forget?
Yeah, the ones that.
So the integral gods are happy, but the math teacher is not.
Well, all you have to do is.
We forgot to what? Balance it?
But all you have to do
So-
now is multiply the
so what are we
1/3
missing
by
right here?
1/3.
Oh, 1/3. Okay.
So it should be like
Oh
2
man.
nights.
Okay, so that's 2/3 times 1/3 is 2 nights.
Uh-huh.
Yep.
I was doing so well.
Sweet.
Okay, and if you wanted to, you could put that back in radical form, but at this point, we all know how to do that, right?
Yeah, I wrote mine to square root of 3x minus 7 cubed over 9.
Yeah. But I don't require you to do that. Oh, that is pretty though. Yeah, so if you want to go back to radical form, just as long as you can recognize back and forth, it's no big deal. Thank you for catching my glaring error. So let's break right there and then we'll look at some of the more complicated inner derivatives.